This is the pre-lab talk for Experiment 1 in Chem 120, Introduction to Graphing. The goals for this experiment are threefold. The first goal is to allow you to explore the criteria for what makes a graph a good graph. You'll do so by evaluating graphs that were drawn from students from previous terms. These are going to be hand-drawn graphs. You're also going to practice constructing a graph and reading points from a graph using hand-drawn methods and also using Microsoft Excel. These skills are going to become very important as we do look at different experiments this term. You're also going to practice calculating the slope of a best fit linear plot. Graphing is an important skill in the sciences. We use graphs to show relationships between variables measured in experiments, or at looking for data collected due to observation. The graph, for example, on the right is a plot of new COVID-19 cases in Pennsylvania over the past 2 months. The bar graph shows the number of new COVID-19 cases each day over the period of mid-March to mid-May of year 2000. We could look at this data in a table, but graphs also provide a very nice visual representation of our data. Graphs are also very basic models that can provide some predictive power. These models can be made by using mathematical equations to fit the data. The red curve shows a fit of the data of the COVID-19 data in the plot on the right. We can see by the red curve that the number of new COVID-19 cases increased around exponentially over the month between mid-March and mid-April. The number of cases has been slowly decreasing over the past month, as shown by the red trend line. Graphs also can be used to determine important quantities in physics and chemistry. For example, we'll be using graphing methods to determine the delta H, or change in enthalpy, and delta S, or change in entropy, for the solubility of potassium hydrogen tartrate, or KHT, in a later experiment. Let's look at the basic features of a graph. In a graph, we usually plot two related variables. One variable we call the independent variable, and the other variable we call the dependent variable. The independent variable is typically plotted on the x-axis, or horizontal axis. This is the variable that we are controlling or changing during our experiment. The dependent variable is the variable that we're measuring as a response to changing the independent variable. We usually plot the dependent variable on the y-axis of our graph, or vertical axis. We use our axes to plot the data, but we first have to develop a scale for our data. Some criteria for determining our scale is as follows. We want to make sure our scale spreads out the data so that it takes up most of the plot area. We usually choose our scale so that they're nice numbers, or easy to read numbers. To do so, we usually want to choose a scale in which the tick marks are multiples of 1, 2, or 5. This means that multiples of 100, multiples of 10, multiples of 20 or 25, or even multiples of 4 are pretty good scales to use. Also, you might notice that the origin is not shown in this graph that we're making on the right. The origin, or the point of 0 on the x-axis and 0 on the y-axis, doesn't need to be always shown in the graph, just depending on the values for your data. Note that we're showing 0 on the x-axis because 0 is in proximity of the data that we're going to plot. However, we're not showing 0 on the y-axis because it is far away from the data that we are going to plot. When we plot our data, we want to use the scale that is determined by the tick marks that we've drawn for our graph and the grid markings for the graph paper. Most of the time, the data will not fall on a grid line or tick mark. When we plot our data, we plot our points so that they're easy to read and big enough to read. And we make sure that the values plotted are accurately represented on the graph. Once we plot our data points, we can also draw a trend line through them. We call this a best fit line or best fit curve. The best fit line or curve is a curve that represents a mathematical function that best represents our data. In our General Chemistry 2 lab course, we'll basically be looking at linear fits. Therefore, we want to draw the best line through our data. Notice that this line does not connect the data points. Merely, it best falls along the data points. Connecting the data points have very little to do with looking at the trends that we want to explore. Also notice that the best fit line, depending on our data, does not necessarily have to pass through the origin. The line that we've drawn represents a linear equation. The general equation for a line is y is equal to mx plus b, where x and y represent the dependent and independent variables used in our plot. M is the slope of the best fit line, and b is the y-intercept. The slope and y-intercept may represent important values to us, as what we discussed in the experiment that we're going to do looking at the solubility of KHT. Therefore, it might be important to be able to calculate the slope. Once you calculate the slope, you will be able to easily determine the best fit line, or the y-intercept of your best fit line. To calculate the slope of your line, you want to choose 2 points on the best fit line. Notice that we're choosing points on the best fit line and not data points. You want to make sure that you choose points on the best fit line that are far away from each other. The slope is calculated using these points. You might remember from your algebra classes that slope is equal to rise over run, or the change in y over the change in x. You can use the 2 points selected from the best fit line to calculate this by determining the difference in the y values for your points and dividing it by the difference in the x values for these points. These are basic ideas behind preparing a graph of your data points that might fit a linear equation. As mentioned, the slope and the y-intercept might be important, may represent important values, such as the enthalpy change or entropy change, in the solubility of KHT experiment that we will do. We went over ways to hand draw a graph, which we'll be practicing in this experiment. But more practically, you'll also be drawing graphs in Excel. It is important to note that when you make a graph in Excel, you're going to use the basic features that we talked about in a hand-drawn graph. That is, you'll want to plot your dependent variable versus your independent variable on the y and x axes respectively. You want to make sure that your scale allows the data points to take up most of the plot area. And you want to make sure that your data points are easy to read. You'll also take a look at some other features when graphing in Excel as you do this experiment. For example, adding grid lines so that you can easily read the points on your graph. You'll also be able to easily insert a best fit line. And the slope and the equation for that best fit line will be automatically calculated for you. Graphing in Excel also gives you some other important statistical information about your graph that might help you in evaluating your experiment. For example, you'll see that on this graph of Gibbs free energy versus temperature, we also calculate what's called the R-squared value, or correlation coefficient. This value is usually between 0 and 1 and allows you to determine how well your data fits how well your data fits with your best fit line. A correlation coefficient that's closest to 1 means that your data, the best fit line, provides a very good fit for your data. If you see a data point that is very far or not well correlated with your best fit line, that might mean that you either plotted the data incorrectly or that experimental run needs to be repeated. Now you're ready to go off and practice looking at the features, evaluating the features of graphs, and practicing making graphs in both by hand and in Excel.